All right, so let's get started in our second section of Chapter 11. We're going to deal with the first law of thermodynamics, and we're going to specifically go through refrigerators. So remember, thermodynamics is the name we give to the study of processes in which energy is transferred as heat and work. So those are the two things that we're going to really focus on, heat and work. Remember, heat is going to be represented with Q, work is an uppercase W. So remember, heat is the transfer of energy from one object to a second one at a lower temperature. Thus, heat is much like work. To distinguish them, heat is defined as the transfer of energy due to a temperature difference, whereas work is the transfer of energy that is not due to a temperature difference. Remember, work we have worked through before, force times distance. We talked about pressure and changes in volume. Those are all representations of how we can understand work. In these problems, we're also going to think about the work and heat that is transferred in and out of a system to the environment. So we're always going to focus on something very, very specific in our questions. That is going to be our system. So the other variable that we're going to see in these problems, work, heat, and also internal energy. So remember, internal energy of a system is the sum total of all the energy of the molecules in the system. Remember, the internal energy is going to be directly related to the temperature, the average kinetic energy of those molecules or atoms. We would expect that the internal energy of a system would increase if work was done on the system or if heat was added to it. Similarly, the internal energy would be decreased if heat flowed out of the system or if work were done by the system on something in the surroundings. So we have to remember that, or we have to understand the mathematical relationship here between our internal energy, heat, and work. And this is represented by this equation, delta U equals Q minus W. Now this is really, really simple, right? That the change in internal energy is going to be represented by the heat minus the work done by a specific system, right? Always focusing on the system. But it gets more tricky when we have to assign a sign, positive or negative, to these two values. And this is where table 11-1 is going to help us out. So I want you guys to turn your books or open your books to page 410, table 11-1. And so the first one here, we're focusing the first 3 rows on heat, the last 3 rows on work. So if we're going to have a positive Q is going to be greater than 0, energy is added to the system by heat. Okay, energy is added to the system. Energy is removed from the system. We're going to have a negative Q less than 1, and no transfer of heat is going to be represented by, or Q is going to be set to 0. So just hop over to the next page, 411. So remember this term that we talked about in our last video, adiabatic. No energy is transferred by heat. So Q is equal to 0. So we're going to see these adiabatic phenomena, these special processes, in our next section, or the next slide, when we talk about how refrigerators work. They're going to undergo these adiabatic processes in order to cool down the interior of our refrigerator. So let's go back to table 11-1. We're going to look at work next. So work done by the system, work is going to be greater than 0. We're going to have a positive W value. So we're going to look at, again, we're focusing on gases. Gases expand, gases can be compressed. The refrigerant in our next example is going to undergo compression, expansion, vaporization, and condensation. So gas is a really easy thing to work with in these sorts of systems because gas is easily expanded, easily compressed, So expansion of gas is going to be work done by the system, a positive value. Work done on the system, a compression of gas, work is going to be a negative value. If no work is done, W equals 0. Okay, so those values, those signs are going to be useful when we look at example problem. So skip over, turn to page 412. First law of thermodynamics. So I want you guys to spend some time looking through this example problem. A total of 135 joules of work is done on a gaseous refrigerant as it undergoes compression. So we are going to compress, this gas. So we're going to say, skip down to number 1, define. Work is done on the gas. We are compressing that gas. So work is going to be done on the system. And so that's going to lead us to a sign for W. That's going to be a negative 135 joules. Work is done on a system. So work is going to have a negative value. If the internal energy of the gas increases by 114 J, right? So that's going to be a delta U. What is the total amount of energy transferred by heat? If these two values, work and delta U, are not equal, which they clearly are not, Q, heat, is going to be also part of that equation. So we have to figure out our Q. There's the diagram that's helpful. Again, compression, this is a piston inside of a cylinder. Work is done on the system, 135 joules. We assign a negative value. U is so the internal energy is changed by 114 joules. And then it's asking you that Q with the 2 arrows, which way is the heat going to flow? And so that's really what we want to think through here to make sure that we have the right value for Q. Again, this equation that we use, delta U equals Q minus W, is a really simple example, really simple equation. But again, the signs get tricky. Okay, so we're solving for number 2, we are rearranging, so we are solving for Q. We now rearrange Q equals delta U plus W. We plug in those values, and we end up with a negative value, negative 21 joules. So the sign for the value of Q is negative. Looking back at that table, a Q less than 1 indicates that energy is transferred by heat from the refrigerant. Okay, so again, why is W and delta U different? We're going to see that energy is transferred from the refrigerant to the environment through a heat transfer. So number 4, although the internal energy of the refrigerant increases under compression, more energy is added by work than can be accounted for the increase in internal energy. This energy is removed from the gas by heat, as indicated from the minus sign preceding the value of Q. So we're going to work through an example problem here together in our next section. All right, so let's get to our example problem. 2,500 joules of heat is added to a system. 1,800 joules of work is done on the system. What is the delta U for the system? So thinking about what is this problem telling us? On the system, added heat. So we should intuitively think that we would have to add the amount of heat and the amount of work in this problem. But we have to remember our equation here. Delta U equals Q minus W. But if we are going to add these two values, what is going to be the sign for W? So let's think about it. So Q is equal to a positive 2,500 joules. Work is going to be equal to a negative 1,800 joules. Now remember, go back to table 11.1, and again, look at this explanation. Work is going to be less than 0. Work done on a system. So it's a little bit counterintuitive. On a system, is going to end up having a negative value here. So delta U equals Q minus W, 2,500 joules minus a negative 1,800 joules equals our value of 4,300 joules. And again, that's going to be positive. Work added or work done on the system, heat added to a system, we would imagine and agree that is going to be a positive value. Okay, so this section, we're going to break this section into two. We're going to talk about refrigerators, how they work, and then we're going to, in the next video, talk about heat engines and then the efficiency of engines. If you guys are mechanically inclined, you should know that an engine is extremely inefficient, and we'll talk about the calculation for that in the next section. But it's actually kind of cool to understand how refrigerators work. We all kind of take this technology for granted. I certainly do. And so again, we're thinking about these three variables, Q, W, and delta U, coming from our equation. And I have a figure here, which is also going to be very, very similar to figure 11-10 at the bottom of page 414. So they use letters. In this diagram, they use numbers. It's all going to be the same thing. Also, we have values, again, positive, negative, or 0, assigned to these steps so we can understand them in context of energy transfer. So remember, Q, when it's set to 0, is adiabatic. So we see that there's two adiabatic processes here. We see that there are some sections where work is not going to be done at all. And then we're going to see how this all plays out into our delta U value. Okay, so we're starting at number 1. So we're going to start down here at the evaporator and the cold refrigerator space here. So we're going to see that the system is this, right? The system is the refrigerant in these coils that are going to go through this specific cycle. So we call this cyclic because the temperature that we start at is going to be the temperature that we end at in our system. Okay, so this is going to go through a cycle similar to what we'll see in a heat engine. And so we have our refrigerator. We want to maintain that cold temperature. And so we're going to allow any heat to be transferred from our refrigerator to the coils inside of the refrigerator. And so we know that that anything, if you just went shopping, you're bringing in your room temperature groceries, you're putting in some Kool-Aid that you want to cool in the refrigerator. Well, that Kool-Aid is going to be at a higher temperature than what you want it to be, right? You want to cool it down. And so the heat is going to be transferred from that Kool-Aid to your coolant in your refrigerator. And so at this point, your coolant is liquid inside of these coils. This is going to be a very special type of liquid. This refrigerant is going to have an extremely, extremely low boiling point. So what does that mean? That it's not going to take a lot of heat transferred from the interior of your fridge, right? Your Kool-Aid, that is room temperature, going into your fridge is going to be enough energy to boil that liquid off, right? So we're going from a liquid refrigerant to a vaporized refrigerant as heat is transferred from your Kool-Aid, your room temperature Kool-Aid, to the coolant. Okay, so the low temp of the refrigerant allows warmer air in the fridge to transfer heat to the coolant. Increasing the temperature of the coolant brings it to a boil. So now we're going to the next step. So we have vaporized our coolant, and we're going into a compressor. So we had a heat transfer in number 1. We're going to have a work input in step number 2, or letter B. And so work is done by a compressor to compress the gas. This is done without a heat transfer, so this is going to be our adiabatic. So let's go over here. I forgot our little table here. So in our first step, or in letter A in your book, we had heat transferring to our system. So that is going to be a positive Q. No work was done by that system, and so we have an overall increase of our internal energy. In letter B here, we're going to have no heat transfers. This is an adiabatic process. We're going to have work done on the system. We're compressing that gas, so work is negative. And so again, we're going to have an increase in our overall internal energy. So once we've compressed that gas is going to, so the compressed gas moves to the condenser at the back of the fridge, which is in contact with the cooler outside air. So again, we're going to have a temperature gradient. Temperature gradients is when heat is transferred. So now we're going to have heat loss of our system. So here we have Q is going to be negative. Our heat is removed from the system. No work is done. Nothing has actually physically been moved. And now we have an overall negative value for our internal energy. And then the final step, they go through these coils. This is at the back of your fridge. This is why your fridge feels hot. Your internal part of the fridge is cold, and the back of your fridge is hot, or your freezer. That is because of this heat transfer. So now we're going out. Our final step is when this refrigerant is going to do work, right? Work is being done by the system. And so it's going to go through this expansion valve. So work is going to be done by the system. That is a positive value. This is going to be done adiabatically, so no heat is transferred. And again, it's going to be a negative U. And then we return back. This is a lower internal energy. This is going to allow, this lowered value is going to allow us to go through the cycle again. This is going to allow heat to be transferred from the inside of our refrigerator and be transferred from whatever warm object you put in there into this gas. Okay, so hopefully you guys will take some time to really understand it. It's actually a pretty neat process. Well, again, we'll talk about heat engines in the next section.